reconnect
and share again. Be this one. Yes, statistical analysis of fatigue data. So we'll discuss a bit and briefly on the methods that are used. Let's see. Share again. That are methods that are used for the fatigue analysis, for the statistical analysis of fatigue data. I'm trying to take this out, but let me stop sharing and share again because it's this one. Okay. So we've seen before that there is significant scatter in composite materials. And depending on the material, again, it might be adhesive or it might be laminate. There is a statistical, the significant scatter, and there is a need for statistical methods to consider about this scatter. So we know that there is scatter in the static results that we are using, and also is a scatter in the fatigue results. And the definitions that we'll use today are summarized in this slide. We have the mean SN curve, actually is the linear regression, the fitting to the experimental results. There we have the tolerance bound, which is the depending on the percentage that we need to set for this, it's the bound that actually closes the experimental results in between the lower and the upper bound. We have the probability of failure that is defined by Weibull or other type of distributions that we can fit to the experimental results. And probability of failure is 50% when we are in the middle of this line, and it becomes less when we go to the left, and it becomes more when we go to the right. Of course, other statistical measures like confidence level are introduced in this in this analysis, which is actually the confidence level is how far we are from the critical regions of the statistical distributions that are used. So in ASTM and in other standards, there is a kind of recommendation again for the repetibility or the replicability of the results. How many specimens we need to test to be sure that we have a statistically correct data sample. And ASTM gives this kind of equation to calculate this. Percentage of replication is total number of different stress levels used in testing and total number of specimens tested. Actually, here it shows that if you test in different stress levels, you cannot test 20 specimens in one stress level and one specimen in the other stress levels, because then you don't have a balanced sample. You should be somehow your specimens should be well distributed along the SN curve. And
yes, I just have one comment, maybe a question here, that most probably the ASTM, this 588, while suggesting this formulation, assumes that the fatigue life data is log normal distributed, if I remember it correctly. Many a times we see that the fatigue life scatter data, or the data itself is not following the log normal distribution, and then we find some issues with this particular formula also, which is although a part of the standard anyway. It is a very old one, which is there.
Yes. Yes, this somehow confirms or validates the discussion that we had before, that standards are there to give some recommendations. It's how can I say in simple words, like nice to have. Huh? This is what we can do with standards. Here it says
better than nothing. Better than nothing.
Exactly, better than nothing. So if you see the standard itself, says that you need at least 75% of data of replication to have reliable data. This doesn't mean that if you have a replication of 70%, you cannot have reliable data. And again, the standard says that between 50 and 75%, you can this number of replications is sufficient for design allowables. And this for me is contradictory because it says that if you are below 75%, you do not have reliable data. But then the standard says that if I take word by word what I said now, it says that if you do not have reliable data, you have sufficiently correct data for design allowables. Which you see, it's a paradox. Huh?
Most probably they are taking two large design allowables later on, so that it is all merged. That this errors because of these may not will be covered most probably with high factors.
Exactly. And then if you see, for example, again coming back to this, here we talk about replication, but then the same standard says you can test between 12 and 24. This is 100% difference, 20 and 24. So either you test 12 or 24.
12 or 24.
You can have 12 with a very good replication because you can spread 12 specimens in 3 stress levels and each one has 4. So you have more or less 100% replication. And you can have 24 specimens and your replication might be 30% because you have 20 of them in one stress level and the other 4 you just distribute it in different stress levels. So this is, again, a kind of guideline, more or less you need, and we know now that you cannot build a nice, reliable SN curve without having at least 12, 15 data points. So this is experience then that tells you, okay, my test is okay, even if I'm not following religiously these recommendations of the standards. So this is, yes, I don't know why this slide is here. So for the statistical analysis, we have, as we said, the normal lifetime distribution, which is not the standard that we are discussing, but it is the typical standard that is, or the typical distribution that is used in even in static loading. In concrete, you know that you calculate the characteristic properties. So this is what I call here the normal lifetime distribution. Then we have the ASTM standard practice. And then for composites, we've seen in the 1980s, actually these were 2 papers in the same STP, standard testing procedure from ASTM, where both Whitney and Sendesky suggested methods to improve, if you like, the statistical analysis of composite. They were telling in the papers, they were mentioned like statistical analysis methods for filamentary composite materials, so composite materials with fibers in the loading direction. So there I will start and go briefly in both all methods. Normal distribution is as we said before, it's a very simple equation that actually allows you to estimate the characteristic value of property. And in this case, if we talk about numbers of cycles, because this is the objective in fatigue, we can estimate the characteristic numbers of cycles, of fatigue cycles. And of course, we can use any reliability level. And this characteristic number of cycles can be used instead of the average number of cycles in the typical SN curve to produce the reliability-based SN curve according to this methodology here. Next, we have the ASTM, the ASTM 739. It has been established in 1991, so 30 years ago, 35 years ago, and has been validated in 2004. And this standard assumes a log normal distribution for fatigue. Log normal means that the logarithm of the fatigue cycles are normally distributed. Assumes that the variance of the fatigue cycle is constant. and this is important, and that's why I have it highlighted here, it assumes that the dependent variable is the number of cycles and the independent variable is stress. And I have it here because a lot of times we do mistakes when we plot stress number of cycles. We plot our points here, and this is experimental points. And then we go to Excel and we say fit a line. And then Excel fits a line and it gives us an equation. And in the equation that we get is sigma alpha or sigma max, whatever is this value here, let's say that it's sigma alpha, equals number of cycles, it's sigma 0. Here, I cannot clear. Wait. Okay. It is sigma alpha equals sigma 0, number of cycles to the minus 1 over k. So when we fit like that, we consider that the number of cycles is the independent variable, and sigma alpha is the dependent variable. And the standard requests the opposite. So what we have to do to get the correct value is to plot actually number of cycles with stress, plot the data in this format, and then fit a curve. And this curve should be then inversed actually to give the final equation, that is, so to define the requested model parameters. If you do this as an example, as an exercise at home, you will see that the curve that you fit by using this model, so this procedure compared to the curve that you have here, is a bit stiffer. It gives you a curve like that. And this gives a small difference, but if you want to follow the standard requirements, you have to really pay attention to this small line in the standard that says that the dependent variable is the number of cycles and not the stress, the applied stress level. So then, if you do this, you have the linear or linearized relationships with following the assumptions of the ASTM standard. Can be, if the assumptions are validated, then you can show them in this format. And y here is logarithmic of number of cycles. A and B are the parameters that need to be estimated. And then it suggests for the estimation to do a maximum likelihood estimator, to use maximum likelihood estimators to estimate B and A, and also recommends a specific equation for the variance, which, if you remember what we mentioned in advance, it assumes that the variance is constant. You have to calculate it like that. And then if you have all this, you have an equation for the confidence limits. So you remember the two lines that we draw on top and bottom, and the linearity condition. It says that your condition for linearity to validate that you have linear behavior, you should follow this condition. Parameter f, this f here, is taken from tables that are given in another, this is another point. The tables are given in another standard. So, as I said, we have also Whitney's pooling scheme. Whitney is this publication in fatigue characterization of composite materials in the STP 723 in 1981. So Whitney suggested a very simple model. I will explain it a bit briefly now. That is based on the assumption that you have a power law equation for the fatigue data, which is, as we've seen, it is a correct assumption. And it also assumes that there is a two parameters viable distribution that can fit well the time to failure, which is also valid, as we've seen. So Whitney suggests to fit this viable distribution to its stress level. So you go to each of your stress levels, you take the data that you have there, and you fit this viable distribution. So already by accepting this, you understand that you should have more than 3-4 data points per stress level. You cannot fit a viable distribution if you have 1 or 2 data points. The minimum is 3. The desirable is 7, 8, 10 at each stress level. So by doing this, you estimate the viable model parameters per stress level. And this I defines stress level. And then you normalize all the number of cycles per stress level by the average cycle at this stress level. And like this, you have a pool of data. And that's why it's called the pooling scheme, because you bring all the data to one data set that corresponds to the entire data that you have from the experiments. And there you fit again a new viable distribution for this now Q, which is the pooled data set. And then the condition there is that this Q should be, this N should be 1. If it is not, you have to go back to be unity. The Q has to be unity for a perfect fit in this case. If it is not, then you have to go back, correct your values of cycles with this equation. So the Q that you calculate is not 1. So multiplies the Ni. You bring this Q by Ni in this case here. You estimate a new Q, Ij. You come back here, you do the fitting again. You do this as long as Q0, so the estimated value here is becoming 1. If you have this condition, it means that you have already defined this alpha F, which is the coefficient for the entire data set. And by having this AF, you can fit and you can establish, if you like, your SN curve according to Whitney's scheme by following this equation. So Sendesky, another model that was, you see, it was the same, again, STP 734 in 1981, and it was called Fitting Models to Composite Materials. So for him, fatigue data can be classified in four categories. And this has been done by following, he was following this SLERA concept. I don't know if you remember the first day. Let me open this. The first day we discussed about this SLERA concept, which tells that SLERA is the stress life equal rank approach. And this method says that the specimen that is expected to perform better in static loads is the same that will perform better in fatigue loads. So, and this is the visualization. The same distribution of specimens can be used for static and fatigue. So by doing this, Sendesky tried, with this method that we'll describe now, to transfer all the fatigue testing to an equivalent static strength test.
I just have one again question. SLERA approach is one of the biggest deficiencies, which we say is in the statement itself, that the composite or the specimen which is good in static strength is also good in fatigue. But we don't know. The one which has failed here, the one which has failed is already failed. So you cannot have the same specimen tested in fatigue and the same one in static. So in a way, there is again a big issue which I find every time is there. And that is what, because you have one specimen and it is good, very good in static test, but it has failed.
Yes.
So we don't have the same specimen
You
again.
cannot, exactly. You cannot do you cannot break the specimen twice.
Twice, yeah.
I agree completely with you, and this is exactly why we call this a stress life equal rank assumption, and it's not
assumption,
life equal rank validated theorem or whatever.
It's an assumption, but which has a lot of questions.
It is an assumption that we have also strong arguments to believe that it is a correct assumption, because you can expect that the specimen that is strong in either in tension or in static tests or in fatigue tests. This is something that is reasonable to assume. That's why we adopt this assumption. And this assumption here helps for this model to summarize all the results, because if this assumption is not correct, then you cannot summarize the results. You cannot mix the causostatic results with the fatigue results. So to summarize this, for Sendesky, all the data that we have when we do testing can be considered as fatigue data. So even static strength data for him are fatigue data. Fatigue failure data, so the typical data that we have when we load the specimen up to failure, these are considered fatigue data. Runouts can consider as fatigue data. Runout is a test that you do a fatigue testing, and then you realize that the specimen does not fail after a certain number of cycles. After a couple of million cycles, you say, okay, now I have to stop with this test because I cannot break the material at this stress level. So you just interrupt the test and you don't do anything. And then you have the residual, here I miss an L, residual strength data, which are the data that you can have from either a run out, if you take the specimen that runs out and you test it in static, you measure the strength of the specimen, and this is what we call the residual strength. And the info that you convey with this testing is the strength, so the residual strength, the cyclic stress, so which was the stress that the specimen has been tested before in fatigue, and how many cycles the specimen survived or sustained at this certain cyclic stress. So you see that runouts can be used as residual strength data if you do an additional causostatic test. So how does this work now with the assumptions that he has? Again, logarithmic plot or linear, any type of equation, but it should be a deterministic. And in this case, we use the power law, so the log equations. The Slera assumption, as we said before, and the static strength data that are used follow again two-parameter Weibull distribution, as we know that this is correct. What is important here to confirm is that the static strength data that are used are estimated at loading rates relevant to the loading rates that we have in fatigue. So this is what we discussed before, that especially for our materials that are not very that are not like carbon, for example, unidirectional carbon materials, and we have materials that are more sensible to loading rates. And you've seen before the sensitivity that we have for creep and fatigue and relaxation phenomena. So in this case, we have an effect of the loading rate on the static strength data, and we should secure that the static strength data that we use for this analysis are taken at the same or similar loading rates than those under fatigue loading. So in this case, the model works in a simple manner, but it needs an optimization procedure. So the first part is to transfer all the data to an equivalent, this sigma epsilon here, sigma E is an equivalent static strength. So we have data that either failed or their static strength data, or residual strength data like sigma R, and they are all transferred to this equivalent static strength. So imagine, to simplify this, to give an example, if you have a data point that failed in fatigue, it means that this is 0, you don't have a residual strength. And then automatically you have sigma epsilon, so an equivalent static strength, equals to sigma max by 1. If you simplify this, it gives you this equation. So all the data then are at the end of the day, you have one data set which is only related to this equivalent static strength data. Then you fit again, a viable parameter to this pooled, again, data set, and you define the model parameters. When you have the model parameters, you can plot the SN curve by this simple equation for any, this is now your reliability level. If you put 50% here, you estimate the median curve and the black line that we've seen before. If you put 95% here, so 0.95 in this case, you will plot the SN curve for 95% reliability. So this is how this model works. So if we see the application of all the methods to the first material that we've seen and that we characterized a lot, we see, first of all, again, here the discussion comes to the slopes. All models estimate similar slopes. And in this case, we didn't use any static data. So for the static data are used by the method of Sendesky. And in this case, because we didn't have a lot of static data at similar stress loading rates as the fatigue data, we didn't use. So since we didn't use static strength data, the results that we have are valid for the purely fatigue region of the testing. So for cycles between around 1,000 cycles and 1,000,000 of cycles. Comparing the slopes of our material to slopes of materials that we can, find in the literature, we see again different materials now: glass, carbon, epoxy, glass, carbon epoxy, peltruded bonded joints, even the joints that we've seen before. What is interesting to see is that most of them follow similar values. We have slopes that are more or less around 0.05 and 0.1, which gives again validity to the discussion that we had before about the modeling techniques that we are developing and we use that can be used in any material, and the only thing that has to be adapted is the model parameters. So there the application of the methods to our material, I selected a couple of them. So here is the material for 15 degrees, R equals 0.1, tension fatigue. We plotted the ASTM. So the dashed dot line is, let me just take a pen to identify here. So this is the ASTM median curve. This is the ASTM here for 95% reliability, so the lower bound according to ASTM. This is the line for the characteristic values of cycles. This is the line for Whitney and Sendesky, 95%. We see that they are similar because they are more or less based on the same wear-out model. The model that they are followed, both follow, is the model established by Han and Kim in 1975-6. So it's a wear-out model. And that's why both of them give similar results. And we see also that in this case, ASTM modeling is giving results that are not conservative, which might be dangerous in design procedures. The lower confidence bound of ASTM is already at levels where probably they're not acceptable for design. So next comparison, the same material system, but 45-degree specimens are compression loading, and also 90-degree specimen tension loading. Similar discussion and similar conclusions. We've seen in these cases Sendesky. I will discuss a bit on this, that Sendesky is giving an equation that is not a power law equation, like for example the equation from Whitney or the equation from ASTM, but is giving an equation which is sigmoid. And this, if I go back to the equation itself, it is sigmoid because it has exactly this parameter here. Sorry, it has this parameter here, this C. Actually, the parameters, I will draw the curve. So sigma n. This is the typical power law equation, one slope, and Sendesky gives an equation with two slopes. And this slope here is exactly depending on the values that we have for the static strength data. It is a parameter that has been introduced by Sendesky, this C, exactly to fit the behavior of the material at n equals 1, which is the static strength data. And then the rest of the fitting, if you assume after a certain point, the rest of the fitting is a power law. It is this equation, which is a power law equation. So at this point, we know that all SN curves follow Basquin power curves. We will see also in the next discussion that we have tomorrow on the models how we can use this, how we can improve this performance with additional models, and how we can use this for modeling techniques. So the conclusion for this part, which is the experimental part, is that we know more or less the failure modes. We have identified the failure modes. We know how materials fail, and we try to correlate this failure to the observations. We know that fatigue is a big problem in design of engineering structures, and the experimental investigations that we are doing are multi-objective, depending on the test that we do. And on the other hand, I will set it in that way, depending on the objectives that we have, we should clearly define the experimental program, and we should clearly define the parameters of the program, the experimental program that we would like to perform, to put in place. And then we've seen from these experimental results that I briefly presented here is that there is a big issue also with the synergistic effect of load, environment, geometry, material architecture, artifacts of the testing. All this make the fatigue investigation of composites very much complicated. We know how to address this now, and we know how to do tests, and we also know, we'll see already tomorrow, how to model this behavior. And there we'll see also what are the challenges that are still existing in this area. So I don't know if you're like that. I'm already more or less like that. I would like to thank you all for this, for your patience for today. And probably we can close the meeting here and give again an appointment for tomorrow, same time, no?
Yes, tomorrow